That tiger's not realistic. Okay, go to Staplet. Where are we at? Okay, we're at 2 quantitative variables, and we're going to input that data that they had given us here for what they did on theirs. So they did 0 to 7, and they had this stuff. So we're going to use that as well. And then on your notes, you're going to sketch in that empty space on your notes, you're going to sketch your scatter plot that you get. So this would be rubber bands, distance. All right. Okay, so we're looking at this. Go to Staplet. I want you to sketch this on your notes. So do your best little sketch here to the right side. And we are going to add some outliers and stuff, so that's why it says leave a little room to the right of your graph. So have a little space. All right, and while you're doing that, so the point of this second lesson here is we're going to talk about the S in doves. So we're going to talk about the strength portion. So how do I know if it's strong, and then use words like fairly strong, moderately strong, weak? Like how do we interpret between those? That's what we're going to do here. So yeah, section 3.1 is basics here. You got scatter plots, interpreting a scatter plot, explanatory response, and this thing called a correlation. Okay. So your group's got that. Y'all have this, I guess, since y'all are doing those. So we want to find the correlation, and it's also written as an R value. R equals blank. So on Staplet, there's a nice little spot here that says calculate the correlation. If you're doing this with your calculator, it would be like you would do a menu and you do a linear regression.
Oh, you did linear? Okay.
Yeah, for right now, we're going to do linear. Okay. We can also test if this would be a quadratic or stuff, but we're not going to do that yet. Okay, so I'm going to calculate the correlation, and if you did it on your Staplet calculator, it should have been 0.992. Either way. So R equals 0.992 would be number 2. Find the correlation. So what the heck does this correlation value mean? Let's just see. So how safe do you feel Barbie's bungee jump would be if we actually used this data? So how safe would we be if we actually use this data? So what does that R value actually mean, basically? So R equals 0.992. How safe? So we could even, instead of using the correlation, we could just look at the graph. Like, how safe do you feel predicting just by looking at that graph going up? So I mean, it's kind of going up at a steady rate. I would feel pretty good about getting some sort of guess. Like, this kind of matches our data. Like, we're kind of climbing at a steady rate. So I feel pretty confident about getting a guess of rubber bands. So how safe do you feel? Pretty safe. So we're thinking our correlation, our data is climbing at a pretty steady rate. So what does this value mean? I'm just going to use this empty space here. But your R value, so the R value, the correlation, is anywhere from -1. Maybe I'll do it with this. So less than equal to R, less than or equal to +1. You have a range of an R value from -1 all the way to +1. And so R value at 0.992 is super close to 1. So the closer that we're getting to this value, like 1, maybe I'll just do an example of 1 here. 1 would be like a perfect line going up positively. So 1 would be a perfect positive, and then correlation always talks about linear. How linear is your data? So a +1 would be a perfect line that's climbing positively. The slope is positive. And -1 would be the opposite, and it would be a perfect negative line. So if you are exactly 1, you are basically fitting a line through your data perfectly. So maybe I'll say that, a perfect negative line. Alright. So I mean, I'm feeling pretty confident about it. We're at like 99.992, so we're almost fitting that perfect one. So for what we know right now, it's looking pretty strong. Let's see. So one of the group members snuck an X rubber band to collect more data. Jada Lee was really wanting the biggest one, so she probably snuck out and got 20 rubber bands and wanted to test. Because, it's fine, there needs to be some jealousy, like, who's going to get the best, like, or whatever. So, I need to see y'all at lunch, like, having your own rubber bands and tigers, like, throwing them down, like,
Okay.
this needs to get intense.
Sounds good.
So one of the group members snuck some more data. So we're going to add this data point to our scatter plot. But before we do that, how do you think this outlier will affect the correlation? So adding a point at 1549.
Let's check.
So think about it before you look at your graph. What do you think? Just, you don't even have to say it or write it, but what do you think it might do? And let's see what it does. Let's see. 15. They're not going to let me do it. Okay. So here is our scatter plot. We're putting one at 15 and 49.
Whoa.
And in reality, if I was to make a beautiful straight line like I just did, imagine that is straight, that data point is fitting pretty well inside of it. So what is going to happen to our correlation? Our correlation is saying how does a line fit our data? So is this really going to affect it that much?
No.
Probably not.
That's
Which, yeah, I guess you could calculate point 0.998. Yeah, it actually made it stronger. So we went from 0.992 to 0.998. It actually increased. So the thing here is R. So R is talking about, or correlation is talking about how well does our data fit a line. So we're talking about an outlier here, but if the outlier is in your pattern, it's going to strengthen R. Like if I'm adding more dots into my pattern, it's only going to strengthen my case. So kind of the thing here is you can have an outlier that, so outlier in your pattern actually strengthens your correlation. So strengthens correlation. So not necessary. So this would be an unusual feature. Maybe, I don't know. I got that. It's out there, but it's actually keeping in line with our other data for linear, safe, and it's actually strengthening what I've got. Okay. On this other part, one group member left off a digit, and the 6 rubber band at a point, 6 rubber band is at 6 inches to the scatter plot. How is this going to affect us? So now we're at 6 and 6 inches. So I'm going to have a data point really low. So 6 and another 6. So we got a data point really low here because the person screwed up and they didn't put 16, they got 6. They read it wrong, whatever. So we have this way off data. So what is this going to do to our strength, our correlation? It made our R value 0.838. R equals 0.838. So it weakened it, right? Because, there we go, perfect. So now, if I'm trying to make a line through here, now this is like way away from these other values. So now I kind of almost have to take into account, like, oh, well, that one's way over there. So all these other ones are pretty lined up, but now I'm very confused about this one. If I did some more testing, would I get more lower points? We don't know. So basically the thing here is outliers, outside pattern, weaken the correlation. So not every outlier is a bad thing, but if it's an outlier outside of our general pattern, it does make us question our linear data. Because, I mean, just in general speaking, like, if we're a good statistician in the real world, I don't know, even trying to do stuff on coronavirus that we have no idea about, you know, like something like this, we don't know if this was just a random outlier or if I did more trials, if I'm going to start getting more data points over here, and that might really affect where I'm actually at. So outliers can kind of throw a wrench in our plans. Okay, but we're talking about correlation, our strength. So how is strength measured? It's measured with how well does your data fit a line. That's all R tells you. It's always going to tell you how well does your data fit a line. All right. Unfortunately, the group had measured the lowest point of Barbie's head in inches instead of centimeters. To fix this, they multiplied by 2.54. So they converted, all of us did it in inches, which we did. They converted all of their data to centimeters.
Is the standard, like, for statistics, like, are we expected to do centimeters? I guess it just gives you the unit anyway.
Yeah, you can choose whatever you want. You don't have to necessarily follow metric or standard. Okay. How do you think these changes will affect correlation?
It doesn't.
Why?
It's all changing, not just one value.
It's not like one person
It's
decided
like-
they were going to do it in
It's just
centimeters.
a shift.
Inches.
Okay, yeah, I like that. So when I come over here, hopefully, the thing that's going to change is the distance, obviously, but they should all be getting bigger at the same rate. So if I guess I can plug those in. So yeah, if I'm changing centimeters, maybe I'll just do it roughly. I'm not going to do the decimals. 30, 35, 43, 45, 55, 58, 67, 76. Okay, so yeah, I think, and mine's not perfect because I did not put the decimals here, so that's why it looks a little different, but our correlation, 0.992. So yeah, it's actually still the same even though I rounded, so that's pretty cool. So our correlation, you're right, our correlation does not change when I change units. So if I change our units, if I change all the units, nothing gets affected. So that's a really nice thing if you're like a scientist, statistician, whatever, that I can mix and match. As long as I do something to the whole graph, that correlation doesn't change. Like that would be, like you could even add numbers. If I added 5 to everything, it really shouldn't change because everything got affected. So how do you think these are changes? So changing the thing here is changing units has no effect. What did I didn't even say that on my paper, on my key. Effect? Whatever. I'm not a math teacher. I am a math teacher. I'm no English teacher. I don't like English. Okay. Changing units has no effect on correlation. And y'all's thought process was good, ladies, that we're talking about it, because everything gets changed. Everything gets bigger. So the whole graph is still shifting at the same rate. So the dots are still kind of in the same spot. Alright. Sweet. So everything stays the same. Alright. Changing units, no effect. Okay. Let's go through something and then I want to look at a whole bunch of different R values here. So R correlation, that's basically what we're doing here. So correlation, it can tell us, I'll use some nice stuff here. So correlation tells us direction. It tells us if it's positive or negative. Another thing about correlation is that it's saying how linear is our data. So if I have data that's curved, the R value is still only telling me how linear that curved data is. So, yeah. All right, let's go to how do I say if it's strong, weak, stuff like that. So maybe these are R values here. So R equals -1, 0.5, 0, positive 0.5, and 1. Let's just go through some here. So I said that R equals -1 is like perfectly negative. Perfectly negative. So what I would say, you could even say perfect, or it's like super really strong. Like this is the strongest we're getting here at these ends. So the closer you are to 1 or -1, the strongest you are. And you're actually perfect if you're 1, which isn't going to happen a lot. 0.99 is really strong. If you're somewhere like 0.8, I would maybe say fairly strong. The word I would use for the 0.5, or the ones that they like to say, is like you are moderately strong. So you're kind of, you're not that strong at all, so you're moderately strong. Or you're not weak, maybe. So these two, you could maybe say like moderately, and a 0 would be you have a very weak correlation. So your data is very weak on some sort of linear association. Maybe I'll add some extras in here. So like in between these two, you could maybe say like fairly strong. So we're talking about strength. So you're fairly strong, moderately strong, weak, perfectly strong, stuff like that. So just using some sort of adjective. Is that right? I'm trying to be an English teacher again. I really hate those, like adjectives, pronouns, nouns. I somehow get those verbs, adverbs. I get stressed out when we do that.
So many categories of words.
It made me very, it felt like a dummy. I still feel like, what the heck is this? What's up?
Would 0 not be no correlation? Why is it weak instead of no?
So that you could say no correlation. Weak is the same thing. Like it's just making it like this is the weakest and this is the strongest. So I think if it was exactly 0, you could say no correlation. That would be fine. Okay. What are some other things? Other notes that I have. Oh, here's an important one. R has no units. So your correlation is not like centimeters or inches or feet. It's just how strong is your data in a linear fashion. So R has no units. Changing units. Or you could even flip the axes and it would have no change to it. Like you could flip your X and your Y and those would even have no change. So changing units or switching, they don't really ever ask you about the switching axis, but they could. Switching axis has no change. Alright, I'm going to put a big star here because they definitely asked about this last one. So correlation does not mean causation. Correlation does not mean causation. So just because I see a correlation between two things does not necessarily mean that there is a causation. And I've got a little PowerPoint to kind of show us through some of that. But the only way, so our next unit is how to gather data, and we're going to talk about this more. But the only way you can show causation is with a well-designed experiment. So if you are controlling the variables, you are in full control of your variables, then you can say this caused this. But if you're not in control of it, if you're just observing data, you cannot say that having this causes this to happen. You can only say there's a strong association. So association versus causation, they're not the same. Okay, so the check your understandings are good, but for some reason I always we might have time, but I'm gonna do this other thing first. I always miss out on the correlations, on the check your understandings. Okay. Pause. All right. So here are some just basic examples of saying correlation and causation are not the same. Wearing clothing that promotes alcohol use in young persons or increases the young person's chance of binge drinking. So like just saying that like, oh, you're wearing this doesn't mean that there might be some sort of like, maybe you get some data like, oh, you're wearing this and like this person was drinking more. Margarine, so like butter consumption is linked to divorce. Recent study finds. So like the more butter that you consume, the more likely you are to get divorced. So no, like there's maybe some sort of random association, but there was no sort of like actual butter making you get divorced. But here's the data. Look at it. Look at how nicely they flow together there. Wow. Like, look at the butter and the... Okay. The more ice cream that's sold, the more shark attacks there are. So we need to stop selling ice cream. Why is that happening? Why are there more shark attacks when we're selling more ice cream?
They like ice cream.
Because
Sharks want the ice cream.
in the summer, we're at the beach more. And we're buying more ice cream, but there's more people in the water, so there's a higher likelihood of a shark attack, right? There's like 1,000 people at the beach compared to 10 during the dead of winter. So ice cream does not cause the sharks to attack you. It's just a correlation that's happening. Number of movies Nicolas Cage has starred in and deaths by tangled in bed sheets. This one hurts personally because I broke my arm from being my hands when I was a kid. I stood up in my bed, my brother was playing video games, and I got tangled in the bed sheets and I fell over and I broke my arm because my feet were tangled. So I didn't die, but I did break my arm. Okay. Where's another one? Okay. Sweet. Let me see another one. There was another one that I like. Guess that was it. All right. Oh, okay, yeah. Marriage is causing people to... Yeah, okay. All right. Oh, chicken and oil, those are combined, yes. So they're so nice. Okay, so our correlation, causation are not intertwined together. Just because the data is... Nope, that wasn't what I wanted. Okay, that's good enough. Just because they are together doesn't mean that they are necessarily causing one another. It could just be anything else. Unless we're doing an experiment, then we can say that causes one or the other. All right, this is a little applet that we're going to guess what our R value is. So I just want to give y'all a ton of examples here on guessing what the R value is. So here is our sample of 25 data points. Do I need to zoom in? Okay, there we go. And here is our data. And in your mind, I want you to get a guess at what R value is. And then I'm going to check it. So get a guess. Maybe I'll call on somebody. Megan, what do you think? What do you want me to put as our guess?
I don't know, just because there's so many of them all spread out, but they're all generally the same.
Yeah. All right. Does anyone want to take a guess?
-0.93.
Negative 0.93. And a reason you chose negative 0.93?
Well, it's decreasing, so it's negative.
All right, there we go. I like that. So yeah, it's negative association, so I know it's going to be a negative R value. And then Aletheia must think that these are following a pretty strong linear path. So 0.93. Let's just see what it is. Oh, wow. Wow. Oh my goodness. We did not do this before. Oh my goodness. What the heck? Oh my goodness. We're done. We're done. What the heck? Alright. Alright, all-knowing Aletheia. What's our next guess? Yeah. Oh my goodness. Alright, Aletheia. Yeah, you have to guess the rest because you just got it perfect.
Negative or positive?
Okay, so yeah, what would our R value be? So maybe I'll show you a thought process. So I am seeing,
Negative.
I'm thinking if I drew a line of best fit, it's probably going positive, but it's very, very, very weak. So I'm going to go like 0.2, 0.1. Like it's very low. Negative 0.11, dang it. So they're thinking something like,
That.
it's basically 0. That's what that is. It's very, very weak.
Yeah.
Very weak. That's really bad. Okay, a new one. Oh, what'd you got, Aletheia? Negative? Please tell me.
8.3.
Okay. This isn't Aletheia's fault now. This is now
Yes,
Megan's
it's my
fault.
fault.
Oh, okay.
No, that's
Pretty good.
fine. She led me on the 8. Not my fault.
All right. That's a pretty good guess. So just getting used to R equals negative 0.7. So like here's my line and we're kind of spread from the line. It's not all in a perfect pattern, but it's pretty strong. I would say that was fairly strong negative association between blank and blank with no outliers. All right. Okay, here we go. I like this one. What we got here?
Positive 0.2.
Okay. I think it's going to be really low. Oh, that was actually pretty close. Wow. Okay. Oh, I guess because it's like there's so many low ones here. And then here would like almost have to be my line. I have a high one. I have some low. So yeah, 0.38. So that would be like moderately weak positive association. So we're like past the 0.5. So we're pretty weak, fairly weak, something like that. Fairly weak positive linear association, if you could even say that. Okay. This one again is going to be something close to 0, right?
Yeah.
It's going to be something really small,
Yeah.
0.2. So 0.2 is a really bad correlation, just to get you a feel. Okay.
0.96.
No.
Yeah, this one's pretty tightly grouped and positive. Yeah, 0.9. So we're looking pretty good. So
9.3 was
So it's all about how tight. It's all about how tight to a line is our data. The farther spread it is, the bigger the R value is. Or if you have some outliers, so like this one's not going to be very strong because I've got a point that's pulling our correlation down. Sweet. We still got 5 minutes, so we're doing okay. But yeah, so 0.59 because anytime I have like a low point away from it, it's going to make it weak. All right. Sweet. Weak. So yeah, like I'll just look at the check for your understanding. You don't necessarily have to write it down, but these are pretty decent. So interpret what this correlation of 0.791 means. That just means I have a, fairly strong positive linear association between the chocolate consumed and the number of Nobel Prize winners or something like that. If the people in the U.S. started eating more chocolate, could we win more Nobel Prizes? Yeah. No. We don't know that chocolate causes more Nobel Prizes unless we did some sort of experiment. Nobel.
He said noble. Isn't it noble?
Nobel. Oh, you're right. Nobel. Hey, I woke up late this morning. Okay. What effect does Switzerland have on the correlation? Switzerland's up here. Is Switzerland increasing our correlation or decreasing it?
That's where the Nobel Prize place is.
It is.
That's where they have chocolate. So
That's
obviously
true.
it's gonna be
That's
a
why
lot
they're-
less place
So look, I'm up here, way up here.
And
Would this be hurting my correlation, my positive correlation, or weakening it? Or wait, weakening it or strengthening it? Yeah, it's in our pattern. So this is actually strengthening our correlation. But this one over here, which is Sweden, is actually hurting our correlation. Or Germany. They eat lots of chocolate, but they don't get any of those rewards, so they're hurting it. So if it's in the pattern, it's helping it. All right.